Hello everyone, this is a video lecture for Calculus 3, section 12.3, dot product. So we're finally getting to something that's a bit more practical? Nah, it's formulaic and it's not difficult, but it's a little bit more Calculus 3-like, okay? The past stuff that we've been seeing is definitely review. This is still review, but we're going to be using it much more than that other stuff. Not that we're not going to use it. I think that they're just building blocks. You know what I mean? They're building blocks, and this is an actual, like, moderately big one. So I want to just jump into the very first problem. I think that it's a good refresher. I think it's going to help. There's no need to explain dot product in my mind, but I mean, might as well do one, and then we're all okay and back to normal. So dot product, if you remember, I'm pretty sure this is in pre-calculus, this always results in a scalar, like a number. Like the answer might be 5 or 3 or something like that. So we're going to get a number out of all this. So what do? I'm simply going to multiply my components together, my like components together. So my x's together plus my y's together plus my z's together. You add them all up and you get an answer. So 28 here minus 5 and then minus 3. Put it all together, we get 20. And there you go. Dot product is super easy. Remember always that this yields a scalar. It yields a scalar, which means like a number, like the number 20. It's not 20. It's not 20 comma 0. It's not anything like that. It's just 20. That's the answer. Okay, let's do some more. 12.3.007. So A dot B, and they give me my A and B. I'm just going to go ahead and write it out for you because, well, it's IJK format. So I got 6I plus a J, and then dot, and then I have an I minus 2J, and then plus a K. So notice that I'm missing a K right here. Essentially that's 0. So let me write it out with the alligators. 6, 1, 0, dot, 1, negative 2, 1. And so I multiply like components. 6 times 1, 1 times negative 2, and 0 times anything is going to be a 0. 6 minus 2 plus 0 is 4. So that's your answer. It's just 4. One thing to note, and I've seen this in the previous classes and previous books, sometimes they might just do something like this for your vector, and often I think, oh, well, it's 6, negative 1, 0. That is incorrect. That is 0. It's a 6, 0, negative 1. Notice that's a K, not a J. So you have to skip one. Like, how many J's do you have, essentially? Watch out. I know that this one's not as bad, but sometimes they'll do that on purpose. Okay. Keep doing 13. 12.3.010. So this one's going to start using formulas. Let me go and give you one. A dot B is equal to, it's the same as, magnitude of A times, magnitude of B times cosine of theta. Now, that formula right there is pretty important. I've got a better one here in just a moment. But these are literally identical. Now, let's just not get confused. I use dots all over the place, don't I? So this dot here, that's an actual dot product because, not because of the style of it being like, oh, maybe it's a bigger dot or something. No, it's because I got a vector dot a vector. You see that? This is going to yield a scalar, but each one is a vector, okay? This magnitude is a scalar. It's a distance. It's a number. This here is a magnitude, a scalar, a distance. Cosine of whatever. It's just a number. It's a scalar, number. Scalar times a scalar times a scalar. These right here are actually time signs, okay? Now, if you don't like all those time signs there and you want to just write a, like, hey, let's just do dots whenever there's a dot product, right? Okay, well, let me write it out for you then. There you go. So, like, I get a little confused with these double lines and stuff like that. It looks better in a textbook than writing it. So it's really your call. I mean, heck, you can use parentheses if you really want to, I guess. Like, parentheses around all this stuff. Either way, we're multiplying over here, and that's a dot product on that side. Okay, so here we go. They say that I have an A vector that is, the magnitude of the A vector is 60, and the magnitude of the B vector is 30, and they say that my theta, my angle between them, is 3 pi over 4. And they say find A dot B. Okay, 60 times 30 times the cosine of 3 pi over 4. And if you do all the math, it's 1800 times the negative square root 2 over 2. Again, because that's quadrant 4, therefore your x values are negative. There it is. Of course, you can simplify that to be like 900, I think, but not required in WebAssign. I keep doing that 13. Well, it's 12.3. So 12.3.015. Let me give you another formula. And in fact, I think there might be a new formula almost for every single question as we keep going. So, and that's okay. These are good formulas. It's just a modification of what we saw just a second ago. So let me go ahead and write it out. Okay. Yep. All right. Cosine of theta is equal to the dot product divided by the magnitudes multiplied together. Now, it's kind of weird. Notice I didn't put a dot here. You can. A dot is totally legit right there. You could do a time symbol like a cross, but man, that starts getting a little bit weird because the next section, 12.4, I'm pretty sure is cross product. I'm not 100% sure. I didn't really look at that one. But you don't want to get too confused. I know, it's like, man, we got so many different symbols, you know, we're reusing them all. So just be careful. I just wrote it like this. You're still multiplying these two numbers together on the bottom. Okay? So there's my formula. They give me A is equal to 5, 3, and I got a B, which is 2, negative 1. And they want the theta angle for those. But what's the angle between those vectors? So I got like one vector here, I got another vector there. What's the angle theta between them? Okay. And that was a bad graph. I'm just letting you know. Okay. So notice that there's different components. We got the top and then these two bottom ones. I'm going to just find each of those individually. So the dot product A dot B, I would get 5 times the 2 plus 3 times negative 1. So 10 minus 3 is a 7. So that's a component, that's a piece of it. Absolute value, absolute value, magnitude of A. See, I even mix it up, but it's all the same. We got 5 squared plus 3 squared, so square root 34 essentially. And then magnitude of B is going to be that 2 squared plus 1 squared, square root 5. Notice that I'm not needing to simplify. It's not a big deal. So cosine theta is equal to, my dot product was a 7, and then my two magnitudes were 34, square root 34, and square root 5. We're almost done. Your theta then would be the arc cosine of all this stuff. Make sure that you're in degree mode because they're wanting degrees for this answer. I came up to, actually, you know what? I think this is one answer there. I'm not sure. I have it written down that they want the exact answer. Well, exact answer, there you go. You just type it just like that, and it should work out. Again, 58 degrees about. It's about 58 degrees. It'll go on, of course. Okay, well that was fun. I'm pretty sure they want the exact value though. I emphasized that on my paper. Okay, 12, 3, 0, 29. So this one was this was kind of interesting problem here. I got 4x minus y equals 4, and then I got 2x plus y equals 6. And they want to find the angle between the two lines. Now, I can't remember, I didn't write this on my paper, but they're probably asking for the acute angle between those two lines. I could be wrong. I can't remember. So basically, we're looking for the angle between two lines. Here, let me make up two lines. There you go. They're wanting that angle right there. And I'm pretty sure they want the acute angle. I'm not 100%, but that's my guess. I got an acute answer, so. Anyways, how do we find this, you know, and what do we even do here? Remember that these are lines. Lines are y equals mx plus b, right? So could you do that? Could you move these over here, switch these around perhaps, and get some lines? Yes. Now here's a really good question, okay? Let me kind of coordinate this off. Let's say I have one line right here, for sure. And let's say I have another one right here. Cool. And so we would get this angle right there. What if I shifted that line, had the same slope, parallel lines, but I shifted it right here instead? See, instead of going, I don't know, let's say it was 3, let's say that I'm up at 4 right now. Well, I still want the angle between them. You see that angle right there? Let's just do one more. Let's say I went up to 6. Again, I'm trying really hard to do parallel lines here, okay? See that angle right there? See all those angles? They're all the same. Those are all the same angles. What I'm saying is your vertical shift, your B, doesn't really change the angle that you're going to be seeking. It's really just the slopes. And if you went back to pre-cal, oh, I'm sure that there's a really big formula with m's 1 and 2 and m's, and I don't even know. But there's actually a formula that uses a lot of slopes to find your answer. That's okay. I'm not going to go that route, though. Okay, let me show you the easy way to do this. Notice that we have right here 1, 1, yeah? So let me make these into vectors. You ready? Here we go. 4, -1. This guy right here, you see it? 2, 1. That's it. That's it. Right here and here. Why can I only use those pieces? Because it's the y and x pieces that are important. You don't need b. Just get rid of that thing. You don't need that. It's not going to help you. You're going to get the same angle regardless. If that was a 5, 6, 7, 8, 9, 10, doesn't matter. You're going to get the same angle in the end. So now I have my two vectors, and oh, I remember there's a formula for this. There's an A, there's a B, and then we got our dot product divided by the magnitudes. So there's your formula. Let's go ahead and toss it all in. So A dot B, what would that look like? Again, you're getting a scalar. So 8, again, I'm multiplying. 8 minus 1 is a 7. Magnitude of A, the square root of 17. And then the magnitude of B is the square root of 5. Okay, so putting it all together. Sorry, it keeps going sideways. I'm like going that way. Anyways, I've been using the tablet all summer and into the spring, but it's still not the same as drawing on a whiteboard or on paper or anything. It's just different. Okay, so this is essentially my answer. I could just say arc cosine of all that stuff, and I'm done. It seems like they wanted a approximate answer because I did not box this in. I boxed in 40.60129 degrees. Remember to keep in degree mode. Okay, for at least right now. Okay, that wasn't too bad. This question is different. Very different. And you'll see it, and then you'll move on, and you'll probably never see it again. They're talking about the direction cosines. Direction cosines. And they give me this vector here, 4, 1, 2. And so it's a part ABC kind of thing. They're first wanting cosine alpha. And I'm going to give you the formula. It's a vector, which I don't like using a vector here, because a and alpha, they kind of mix up. Let's do v vector times, and this is where it's weird, I component. So it's dot. I said times. I meant dot. V dot I component, and then divided by magnitude of v, and then dot magnitude of I component. So that's kind of weird, isn't it? And then you would find your alpha, whatever. So what does it mean to have an I component? That's so strange, isn't it? Notice the difference between vector and component. See how I have a little arrow thingy versus a little hat? Those are different, okay? What I'm getting at is that it's v vector dot 1, 0, 0. And then divided by the magnitude of v. But then what's the magnitude of 1, 0, 0? Well, it's just 1. So that doesn't really change anything. So this is what we're going to use as a formula. So let me go ahead and do this. So cosine alpha is going to be now 412 dot 100, all divided by square root of 4 squared, 1 squared, 2 squared. So when I'm doing this dot product here, notice that I'm going to have 4 times 1, 1 times 0, 2 times 0, add it all up, you're only going to get a 4. It's essentially saying what is the x value of your vector. Okay, so that's what it's trying to say. X value of your vector divided by your total magnitude here. And so that's 16 plus 4 is 21. So basically I got 4 over the square root of 21. And this is again equal to cosine alpha, which this is your part A answer. And they're going to want it again for cosine beta and then cosine gamma, I think is what they were using. Regardless, this is like your part A essentially, all this stuff. And you just repeat it for your y component and z component. So I'm just going to put repeat. And then on the second part, you're going to have find actually what alpha is. And so you would say the arc cosine of 4 over square root 21 is equal to 29.2059 degrees. Cool. And then you would repeat again for your beta and your gamma. All right, awesome. That wasn't too bad. You probably won't be seeing that very much as we keep going. I don't remember seeing it much in this class, honestly. Okay, 12.3.039. I got A is equal to negative 815. And then I got a B vector, which is 3, 5. And they're wanting, these are two different things here. They want the scalar projection of B onto A, and you can write this as comp, and then there's a little subscript A vector, and then a regular size B vector. So they want that, whatever the heck that is. And then they want vector projection of B onto A and then you can rewrite it as proj, I guess, little a subscript vector, regular size B vector, and they want that. So what they're really wanting here is a scalar and a vector, okay? And let me give you the formulas for each of these because, well, I ran out of room over there. So your comp AB there is A dot B divided by magnitude of A. That's not too bad. And I don't see us using that a whole lot in this class. You do use this projection a bit more. And it's really easy to explain here. I'll show you a picture of it in just a second. So that's A dot B divided by magnitude of A squared. Magnitude of A squared. So it's kind of funny. This was already square root of blah, blah, blah. And then you're squaring it. Square root and square should essentially cancel. But then you're saying times in a vector. Again, this is a scalar answer. This is a vector answer. Okay? So let me at least show you the projection of B onto A. Or, yeah, of B onto A. So you essentially have two vectors here. This is your A, this is your B, and it's basically like a shadow that falls down here. Now, I actually it's a little bit messed up here. Let me redraw it just a little bit better. And you might be thinking, that's about the same thing. Well, it's got to be a 90 degrees right here to make this thing work. So what you're getting here, this vector right there, this guy, is that projection vector, okay? That's that A onto B kind of thing, or B onto A. So I think of it kind of like a shadow. It's kind of like you have the sun right here, you know, and what would B look like if it were to be flattened onto A? That's basically what's going on, and again, it's always at 90 degrees right there. Cool. So it is pretty important stuff, but again, it just comes down to a formula essentially. So let's do that. Okay, here we go. So comp onto A of B is equal to the dot product of these two vectors. I gave you the two vectors earlier, right? Yeah, okay. I'm just copying it down. And then divided by the magnitude of A. Again, notice I don't have that 8 squared, or that negative 8 squared, it's just 8. Actually, that's the entirety of it. So when you dot product these are multiplied to make a negative 24. Those guys are multiplied to make a 75. So you result in 51. And then divided by square root of 289. You know what's funny is that this actually ends up being 3. Yep. It actually just ends up being 3. So there's your answer, 3. Okay, the projection, a little bit more important here. So I got that dot product again, and I already know what that dot product's going to be, 51. So don't need to waste time on that. And then it's the magnitude of A squared, so I'm going to take this guy. I'm just reusing here. And I'm going to square it, and then I need to multiply by the vector A itself. Well, you know that the square and square root are going to cancel, leaving just a plain old 289 right there. So that was easy. That number in the front ends up being, I don't really know, but it doesn't matter. I distributed it in, and I used a calculator to help me a little bit. Negative 24 over 17, and then 45 over 17. And there you go. Okay, that was fun. Next one. 12.3.046. So here's a new formula for you. The orthogonal of B onto A, the formula is simply B minus projection of B onto A. Okay? That orthogonal stuff that they're talking about is that 90 degrees stuff. Okay, so orthogonal means 90 degrees. So there you go. If you kind of look at it, this is B, right? And this is your projection formula. And so this is probably that orthogonal thing they're talking about. It's that little guy. Regardless, it's just a formula. And so here we go. A, I got 2,8. I got B, 4,6. It's a 6 right there. And so we need to go and find out what my projection is, and then I need to also fulfill this whole formula. So here we go. I'm going to go ahead and use this formula. 4, 6, oops, minus, and then I got to do this projection formula. So 28 dot 46 divided by, and then I had my magnitude of A, and then I'm going to square it, and then I have got, no, it's not A, it's B. Right? Because we're having a B there. No, it's A. It's A. If you go back to the formula, it's an A up there, right? Yeah, let's go back. Yeah, there's A's. I'm sorry. Yeah, it's A's. We're good. I was doing it right. Just second guessing myself. Okay. So there it is. You're done. Well, you got to simplify a little bit, you know what I mean? I wonder if WebAssign will take all that. It'd be funny just to see. Anyways, in the top we got 2 times 4 is going to be an 8. And then we got an 8 times 6 is like 42, 40 somethings. Oh, I know. 48. Okay. Well, I was close. It was 40 somethings. The square root and the square cancel. 4 and 64. Getting closer. Just simplifying this. So my numerator and denominator, they come out to be 56 and 68. What did I do here? I just used calculator. I mean, when I say I'm using calculator, I'm not like putting this whole thing in. I'm saying 4 minus this guy times the 2, you know? And so I came up with 40 over 17, and then a negative 10 over the 17. There you go. All right. One last question. Almost there. 12.3.051. So this is a word problem. It says there's 30 pounds of force applied at an angle of 35 degrees, and it's moved horizontally. Oh, that's pretty bad looking. Horizontally 50 feet. I think it's like a box, or it's some kind of a sled or something like that. So what's going on is you got something, it's being pulled at 35 degrees, and this is 30 pounds, and it's traveled 50 feet. And they're wanting to know, what is the work done? What is the work done on that? And so really it's like force times distance, essentially. Work, force times distance. And so their answer is actually in foot-pounds even. So that's another indicator. You're simply multiplying. Well, let me give you the formula, I suppose. It's kind of like a formula. The 50 feet, the 30 pounds, but then the cosine of 35. What we're getting at is that only the x component here matters. You're not lifting the box up off the ground, so only the x component matters. What is your x component? It's going to be a cosine. So we're looking for the cosine of this. This here is that force, while here is your distance. Multiply it all together, and I got 1228.72806 ... But there you go. All right, we're done. If you have any questions, let me know. Thank you very much, guys. Have a great day.